Hi, this video we're going to cover binary search trees, and I'm going to do it in two different ways, so just stay with me on here. First thing we're going to do though is talk about a binary search tree and how it kind of works, and then we'll work on the code for it. So, this section we will study binary search trees. It's another way to map from a key to a value. In this case, we are not interested in the exact placement of items in the tree, but we are interested in using the binary tree structure to provide for efficient searching. So let me skip down here a little bit because this is not all the stuff we're doing here, what they have there. Okay. Binary search tree relies on the property that keys that are less than the parent are found in the left subtree, and keys that are greater than the parent are found in the right subtree. We will call this a BST property, binary search tree property. As we implement the map interface as described above, the BST property will guide our implementation. Figure 618 illustrates this property of a binary search tree, showing the keys without any associated values. Notice that the property holds for each parent and child. All of the keys in the left subtree are less than the key in the root. All of the keys in the right subtree are greater than the root. Now that you know what a binary search tree is, we will look at how a binary search tree is constructed. The search tree in figure 618 represents the nodes that exist after we have inserted the following keys in the order shown: 70, 31, 93, 94, 14, 23, 73. Since 70 was the first key, scroll up here a little bit, it's inserted into the tree. It is the root. Next, 31 is less than 70, so it becomes the left child of the 70. Next, 93 is greater than 70, so it becomes the right child of 70. Now we have two levels of the tree filled, so the next key is going to be the left or right child of either 31 or 93. Since 94 is greater than 70 and 93 is greater than 70 and 93, it becomes the right child of 93. Similarly, 14 is less than 70 and 31, so it becomes the left child of 31. 23 is also less than 31, so it must be the left subtree of 31. However, it is greater than 14, so it becomes the right child of 14. So to implement the binary search tree, we will use the nodes and references approach similar to the one we used to implement the linked list and the expression tree. However, because we must be able to create and work with a binary search tree that is empty, our implementation will use two classes. The first class will be called binary search tree, and the second class will be called tree node. Actually, I'm just going to use node. Binary search tree class has a reference to the node that is the root of the binary search tree. In most cases, the external methods defined in the outer class simply check to see if the tree is empty. Okay, so I'm not going to use the one that's in here. Okay, so I'm going to go ahead and minimize this, and I'm going to create my own on here. So let me get a blank one started. And I'm going to get this one here out of the way so it's not all bleeding in there. There we go. And so we're going to create the binary search tree. So the first class we need is our node class. So we're going to pass in the key for this. So self.key is going to be equal to key. Self.left is going to be equal to none. And self.right is going to be equal to none. Okay, then we need to create our binary search tree. So in here, our INIT is just going to be self, and self.root is going to be equal to none. Okay, then we're going to do our insert. passing in our key. Now with the insert, this is going to look a little bit different. We're going to use a helper function or method with this. So in our insert, all we're going to do is if our self.root is none, then self.root is going to be equal to node key, else self.root, else self.underline insert, passing in self.root and key. Okay. So if it's not none, then we need to find where it needs to go in here. Okay, so that's going to be our helper insert one that we have here. So that's all we have in there. So now we're going to do our helper one, which is an underline insert, and we use the underline on here in order to keep it private. Okay, it's not really private. If you were in another program that you made an object of the binary search tree and you actually called an underline insert, it would do it. Okay, but it's to kind of keep it hidden a little bit. Okay. So in here, if our key is less than current that we passed in, and current, remember, is our self.root. So if it's less than that, that means it needs to go on the left side. Okay, so so if our key is less than current.key, if current.left is none, then current.left equals node key. Else self.underline insert current.left key, because we found a value there, so we have to find the location under it where it goes. Now, so that's if it's less than. So now we need to check to see if else if key is greater than current.key, if current.right is none, then we insert it. Current.right equals node key, else we need to find the place where it's supposed to go, self.underline insert current.right, comma, key. Now we're going to assume that the value that they're looking for is in the binary search tree. Okay, or the one, I'm sorry, wrong thing. We're going to assume that the value that they're entering in, the key that they're putting in, is unique. Okay, so we're just looking for less than and greater than. If it's equal, it's not going to do anything. Okay, so we probably should print out a message for that, but I'm not going to do that here. Okay, so the next thing is to search for a particular value. And in here we're going to do self and then key, and then we're going to return self.underline. We're going to do another helper on our search, self.root and key. So in our search then we have our current and we have our key. So if our current is none, then we need to check, then we return false because it wasn't there. Okay, there's nothing there. So, but after that, then if current dot key equals equals our key, space in there. There we go. Then we return true because we found it. Else if key is less than current.key, we're going to return self.underline search, passing in our current.left and our key. Else we're going to return self.underline search. I did that twice there, and I also did it up here. And this will be current dot right and key. Okay. So it works the same way as the insert, except we're not inserting, we're looking for it to see if we find it or not. Okay. So if it's not there, then it's false. If they're equal, then it's true. And if it's not equal, we need to see if we got to go left or right. Okay. So now we need to do our, be able to display all this. So we're going to use an in order to do that. And, okay. So we're going to set result equal to bracket end bracket. So we're going to put our stuff in a list and then display it from there. So self dot, we're going to use a helper again. Underline is order. Self dot root and result. And then we're going to return result. So then we're going to do our helper one, our underline in order. So in here, we're going to have if current is not none. So we have something to work with. Self.underline in order, passing in current dot left and result. And then result dot append current dot key, and then self dot in underline in order current dot right and key. So what this does then is it goes down the left side. So as long as there is a current dot left, it keeps going. Once it hits the end and it's not, and it is none, then it goes back, putting the values into result with the append all the way back through, and then it goes the right side. Okay, so let's go ahead and get this saved. And I'm going to save this as a binary search tree.py. Save that. Okay, then I'm going to open up a blank. Whoops, sorry, not open. Do a new file. There we go. So you can do a test program. Okay, I'm gonna make this kind of short. Do from binary search tree import node, and then from binary search tree import binary search tree. Okay. Create our main. So in here we're going to do a BST. It's going to be equal to binary search tree. Our test data is going to be equal to a list. So we're going to do 50, 30, 20, 40, 70, 60, and 80. Okay. For num in test data, bst.insert num. I get everything inserted in there. Then we're going to print in order traversal, and BST dot in order. Okay. Then we're going to print, search for 40, BST dot search 40, and then we're going to print search for 100, BST dot search 100. Okay, so let's save this then. And I'm going to save this as bst test.py. And let's see if this works. Just click on the right thing here will help. Nope, invalid. Oh, misspelled, return false. That would be over here. Right here. There we go. Let's save this. Minimize a couple of things here so I can get to them easier. I need to move these around a little bit better on my, run this again. Another error. In order takes one positional, argument 3 were given. Oh, I didn't put that stuff in there. That should have gone there. So this should have been in here. Current and key. I believe that's what that should be in there. Still another error. Let's see where that was. Self-dot underline in our current left result. Oh. This here. This should be resulted, not. There we go. Save this. There we go. So in order traversal 20, 30, 40, 50, 60, 70, 80, we got those in order. True on the 40 and false on the 100. So great, we got all that stuff working. So now we're going to do this using a dictionary as our values we want to store in there. So I open up a blank one here. And I'm going to get rid of these two because we're not using these anymore. So first we're going to create the node class, and I'm going to do a lot of copying and pasting on this because a lot of it is repeat, and then I'll point out the differences. Okay, so in here we have a key and a value, so we have to add the value in as part of our init. Okay. Okay, this is our insert. Again, we have a key and a value, so we have to pass both of those in here. Okay, and then on the underline insert, the same thing. We have to work with both the key and the value. We're basing everything off the key, But when we actually go to create the node, we have both the key and a value that we're storing in these. So that's the big difference on those. Okay. So let me get my cursor set in the right place down here. And then the search. Again, we're basing everything off the key on the search. And then all we're doing is returning the current value when we do the search on there. So instead of returning true or false, we return none if it doesn't find it. But if it does find it, then we return the value for that key. And that's the main part of that we want to do on there. And then the last part is the display. Okay, so we could have called this in order, but in this particular case, I called it display instead. We still have the result. In this case, I used entries just to change things up a little bit. We still call our in order helper on here that goes through and gets them in the right order to print them out. And we do a key and a value. Would have been better probably if I would have spelt those out, but I didn't on there. Okay, so I'm going to go ahead and get this saved. And I'm going to save this as BST no, wait a minute. Let me see what I've got this saved as. So I do it the same. Yeah, it's BST dictionary, but no space in there. .py. Save. Okay, so now I'm just going to bring over the test program instead of typing it all in. It's kind of short. So from BST dictionary, we're going to import BST dictionary. Okay, and see over here, named it BST dictionary. Okay. We may need the node also. If it comes up with an error, I'll do that. Put that in here also. Okay. So we're going to create a BST dictionary. From our BST dictionary, we're going to insert a banana with 3, apple 5, pear 2, orange 4. We're going to then display all the entries. We're going to put in a key to find, which is going to be pear. And then we're going to call BST dictionary the search to find the key. If result is not none, so if we found it, then we'll print out find, what the key is and what the result is. Otherwise, we're going to print out the key to find was not found. Okay. So I'm going to do that one there, and then I'm going to copy this whole thing again, this one right here, so I can do this Control C. And I'm going to change this from pear to what do we don't have in there? We have banana, apple, pear, orange. About grape. Okay. So let's go ahead and test this out. And there we get. We have all entries in order. We had our apple, banana, orange, and pear. They're in order based on the key, so alphabetical order. Entry found was pear, which was 2, which was true, but grape was not found. Okay, so I hope this helped you out, not just using a binary search tree, but actually using a binary search tree with data that has a key and a value. So it's kind of like a dictionary, but it searches a lot faster than doing this in a list or some other data structure like that. So I hope this really helped you out. Thanks for watching. Bye.